Hello and welcome to the channel. So a square with given side length A is turned around one of its vertices by given angle phi. The objective is finding the common area of new and old positions of the square. Quite obviously phi must be less than 90 degrees, as with phi equal to 90 degrees or above, the squares have no common shape. So ABCD is the original square, vertex A is the center of rotation, A, B', C', D' is the rotated square. The sides of both squares have length A. The rotation angle DAD' has value phi, which is less than 90 degrees. Let E be the common point of sides BC and C'D', and it is required to find the area of quadrilateral ABED'. Let's draw segment AE. This splits the quadrilateral into two triangles, triangle ABE and triangle AD'E. So if we find the area of each triangle, we can find the area of the quadrilateral. Both of the triangles are right-angled triangles with right angles B and D'. Sides AB and AD' have given length A, and if we can evaluate acute angles BAE and D'AE, we can find the areas of the triangles and the area of quadrilateral we need. Try to continue from here. So the right-angled triangles ABE and AD'E have equal sides AP and AD', as well as the common hypotenuse AE. Therefore, the triangles are equal according to right-angle hypotenuse side rule. Therefore, they have equal area. Name it T for triangles. In this case, the area of quadrilateral ABED', which is the sum of the areas of triangles, equals 2T. Also, from the equality of triangles, it follows that angle BAE equals angle D'AE. And let x be the value of these angles. To find the value of T, take triangle ABE. One side of the triangle side AB equals A. Another side of the triangle side BE equals A times tangent of x. Now we can find T as the area of triangle ABE. It equals half the length of AB times the length of BE. After the simplification we get half of A squared times tan of x, while the area we need is 2 times T, or A squared times tan of x. Which is not yet the answer, as it contains the unknown value of x. Let's wipe out the stuff we no longer need and move up the lines we do need. Angles DAD', D'AE, and BAE together form a right angle BAD. The value of angle DAD' is phi, while both angles D'AE and BAE have value x. So we obtain an equation for x and find that x equals 45 degrees minus half of phi. Now we can substitute the expression for x into the formula for the area of quadrilateral ABED' and get the answer a squared times tangent of 45 degrees minus half of phi. However, this formula is not always convenient, as it contains half of an angle. Another formula can be obtained by using the following identity. If you are unfamiliar with that, you should be certainly familiar with the following two identities, appearing at any textbook. And if we divide the first identity by the second, after some cancellations, we end up with sine half of alpha over cosine half of alpha, which is by definition tangent of half of alpha, so the identity is proven. By substituting alpha equals 90 degrees minus phi into the identity, we get the expression for tangent of 45 degrees minus phi over 2, containing an angle complementary to phi. Therefore, cosine turns into sine, and sine turns into cosine. After that, we divide term by term and get secant minus tangent. This gives another expression for the area of quadrilateral: a squared times the difference secant of phi minus tangent of phi. Consider a few examples. For phi equals 30 degrees, the first formula appears convenient. The answer is a squared times tan of 30 degrees, or a squared times square root of 3 over 3. The first formula for phi equals 45 degrees involves tan of 22.5 degrees, whose value isn't known immediately. However, using the second formula, we don't have such an issue. The result is a squared times the difference square root of 2 minus 1. Also, the second formula is more convenient for phi equals 60 degrees. For this angle, the result is a squared times the difference 2 minus square root of 3. Next comes the end of the video.